Okay. I just got the message that the meeting was being recorded. Okay, so let's start with interpretability. So you've probably heard like a dozen different definitions of what interpretability is, but basically we want to be able to understand what in the input makes a model make a prediction. So we have some kind of input, it goes into the model, and we get the prediction. And we want to know, okay, so what in the input made the model make this prediction? And for some classifiers, this is kind of built into the model. Like a linear classifier, you can look at the weights, or if you have like a decision tree, you can kind of follow the yes and no statements. But for other classifiers, this is not as easy. And since we're going to talk about deep learning, neural networks are probably the most known case of these kind of black box classifiers. So by that, I mean, you have some input, it goes into the neural network, and then you get prediction out. And then you can't kind of untangle the relationship between the input and the prediction. Of course, this is not exclusive to neural networks. For instance, kernel methods also have this kind of weakness. So it's a well-known weakness of more complex models. And of course, since neural networks are so popular that they are now, there's been a lot of development on addressing this lack of interpretability. So for instance, this year at CVPR, I think explainable AI was one of like its own track just on interpretability. So I have kind of this example or a little story to introduce you to the concept. So on the left, we have an input image, and on the right, it's kind of the explanation for this image being classified as a horse. So this is kind of a well-known example where they show the use case for interpretability. So the setting here is that this is from a group in Germany, and they had the classifier trained on images of cars and planes and people, and one of the classes was horses. So they trained the classifier and everything worked good. And then they gathered some new images as like a separate test set and tested the classifier again, and it did well, apart from the horse class, which had like a significant dip in accuracy. And they were wondering like why did the horse class decrease so much? And then they started to look into these explanations. And as you can see, so on the right, red indicates that you have pixels that are important to the prediction of the horse class. And as you can see, the horse isn't highlighted at all. The only thing that's highlighted is this tag down in the corner. And what they discovered was that all the horse images in the data set were taken by the same photographer. So you had kind of this tag of the photographer. And of course, neural networks learn patterns. And if you have an easy pattern, you will use that pattern. Horses are much more complicated to classify than just tags. So they kind of removed that part, and then the classifier worked fine. But if you're kind of not too worried about misclassifying horses, then these kind of things becomes much more important when you're working with medical images. So here's another example where they wanted to classify X-ray images of people's chest. So they wanted to distinguish between different types of diseases. But at this hospital, if a person was very sick, they were sent to a different ward to get the X-ray image taken. And at this ward, they added this extra tag on the image. So you can see it up in like the right corner here, like here and here. So the network learned that, okay, if the image has this tag, then it's very likely that this is a very sick patient. So when they got new images from a different hospital that didn't have this tag, the classifier did a really, really bad job. So these are kind of a few examples of where interpretability can really help you evaluate, especially if your model is doing something strange. But like in general, I think interpretability is something that the main point is that you want to make trustworthy models. And as in this medical setting, very few clinicians will if you just give them a prediction, 0.9 probability of a disease, it's very hard to trust just that number. You generally need more. And when we're talking about trustworthiness, another thing that is missing in deep learning is the notion of uncertainty. So well, it's not too much to explain here. How certain is the prediction? And we're going to talk a little bit more about how to model uncertainty in deep learning a little bit later, but I included just an example to show how uncertainty can look and how it can be helpful. So here is an example. So in this case, we have a convolutional network which tries to segment out these small objects. So they're called polyps, and we'll talk more about them later. And then you have the labels. So this is what the network should predict. And then you have the prediction of the model. And as you can see, the model correctly finds the polyp, but it also has this weird big blob towards the bottom of the image. And if you didn't have the last image and you were kind of given these predictions, then if you don't know too much about polyps, you might be, okay, so maybe there is something there, maybe there isn't. It looks a little bit strange. But in the last image, we've modeled the uncertainty of the prediction. So green here indicates that the prediction has a high degree of uncertainty. And as you can see, the polyp itself, like the correct object, has a very low uncertainty, while this weird blob towards the bottom of the image has like a high, everything is very uncertain here. So you would look at this prediction in a new light and go, okay, probably there's been a mistake here. Okay, so I've talked about interpretability and uncertainty, but then the question is, what about uncertainty in interpretability? So essentially, we want to know, we're given an explanation, how certain are we of this explanation? So I have this little example here. We have an image of a cat. And on the right, you can see kind of the explanation for this being classified as a cat. And you can see that there's like many parts of the cat lighting up: the ears, the eyes, the nose, part of the body, like the chin. And the question is, are all of these equally important for the prediction? Are there some that are like, okay, this is certainly a cat feature, and this is more like, okay, maybe it's cat, I'm not sure. And there's not very much work on answering these questions. And of course, this is just an image of a cat, but if this is the image of some kind of, maybe it's a liver or lung or something, then it suddenly becomes more important. So now I'm going to talk about two recent papers where we try to address just this question of uncertainty and interpretability. So first, okay, so we come back to these polyps. And the task here is to segment out these colorectal polyps. So these are images from the colon of different patients. And so we train a convolutional network, and it does a good job of predicting where these polyps are. But then the question is, okay, what pixels are important for locating the polyp? And what we will want is, of course, that pixels corresponding to the polyp are important. And as I mentioned in the beginning, that this the research on the interpretability methods have really like taken off in the last couple of years. So there's many methods to pick from. In this case, we've been working with the method called guided backpropagation. So put it simply, you use gradient information to investigate what features are important. So it's kind of, if you do a little change to the input, how does that change the output, so the prediction? So in this example, you can see on the left, we have the input to the model. Then we have the label, the correct classification or segmentation. And then we have the prediction of the model. So in this case, we do a good job. We find the polyp. But then on the right, we have this explanation for the prediction. And I hope this shows up good on your bigger screen. But you can see, okay, so we have green here that indicates that these pixels are important. But then you also have this area up here, which is also indicated as being important. And that might make you wonder, if you're kind of analyzing these images, you would go, okay, maybe there is something over here in the input that's important. We're not sure. And this is exactly where this uncertainty in interpretability comes in. Are these pixels, are these importance scores as important as these? Certain, sorry. So to address this problem, we proposed a method. So I mentioned that to model uncertainty in deep learning, there's a couple of different methods, but maybe the most popular is one known as Monte Carlo dropout. So basically, you use a method called dropout to model the uncertainty in neural networks. And dropout is a method that you usually use during training of a network to regularize the model and prevent overfitting. So basically, it's called dropout because you're randomly dropping activations in the network. So you can think of it as kind of like a salt and pepper noise. And the idea is that you leave dropout on after you train the network, so during inference. So you can kind of sample predictions. And then hopefully features that are kind of important will always be highlighted as important. So in this work, we proposed this Monte Carlo guided backpropagation method, which basically is like a combination of Monte Carlo dropout and this guided backpropagation procedure. So you have an image and we have a trained network. You pass the image in and we inject some noise. So basically we're reducing dropout. That will give us one prediction. And if we repeat this process, let's say m times, then we get m predictions and we can get m explanations for the same image. And then we can model the uncertainty of the explanations by taking the standard deviation across all explanations. So it's a fairly simple procedure, but let's see how the results look. So if you go back to the same example as we had before, but now we can model it with and without uncertainty. So on the left, that's the same image as I showed you before. We have some important pixels down here and we have some important pixels up here. But now, so green pixels indicates that the pixels are important and highly certain, while red pixels indicate that they are important, but we have a high degree of uncertainty associated with them. And as you can see in this case, that most of the important pixels here are green, while all of these are red, so they're highly uncertain. So when looking at this image, you would say that, okay, so this is probably the important pixels, and we are more unsure about the importance of these. Yeah. Did I want to say anything more here? I think we'll just move on to the, because I think there's been a lot of work on image data and interpretability, but there's been a lot less work on time series analysis and interpretability in that domain. And when you work with medical data, the time series are very, very common. That you have blood measurements, you might have urine samples or things like this. So we just had a paper submitted where we tried to basically model interpretability and uncertainty in time series analysis. So classification of time series using convolutional networks. So I will talk more about the kind of exactly how we did it, but just thought I'd show you an example to see how interpretability looks. Interpretability looks for time series. So instead of indicating what pixels are important for a classification, for a prediction, we are indicating, okay, at what time step, what time steps are important for classification. So in this case, this is an example from like a synthetic data set where we know what characterizes the class. So this is a class which is characterized by having a significant dip at either the beginning or the end of the time series. So you can see here at around time step 120, you have this, significant dip. And in green, it's kind of indicated the important time steps for this prediction. And as you can see, it found the important time steps for making this prediction. So I mentioned it was a little work on time series interpretability and uncertainty for time series. And at least in our experience, this might be because we found them more challenging to work with than images. And there's a couple of reasons why. So for once, when you work on interpretability with images, we're kind of very used to images. Like even if I'm not a medical expert, I can see that, for instance, there's an object present in the image or that something looks strange. But for time series, that's not always the case. You can have kind of, often to interpret like a time series to understand why this is, for instance, a patient that's sick, you wouldn't need medical practice. So In this case, we've had kind of help from doctors at the university hospital here in North Norway to interpret the results. And another point which kind of affects the uncertainty a little bit more is that typically you have a lot less data than you do in the for images. So and that means that, okay, you might train a model, but maybe the model you end up with a model that's not too good. And when you then try to model the uncertainty using, for instance, the Monte Carlo dropout, it's very dependent on kind of the model you initially have. So if you have a bad model, then it's going to be very uncertain across all its predictions. So in this case, we have a little bit of a different approach. For the interpretability, we have been looking at another method, which is called class activation mapping. And without going into too many details, it's a different interpretability method that is designed when you have a kind of a specific convolutional network architecture. So you have this kind of average pooling layer towards the end of the network. And the uncertainty, instead of using this Monte Carlo dropout method, we have been looking at basically modeling uncertainty through ensembles. So there was a paper a couple of years ago at NeurIPS that showed that with actually, you don't need too many neural networks in an ensemble to get good and robust uncertainty estimates. And the good thing is that ensembles are very intuitive. I mean, they can be computationally demanding, but you generally understand, for instance, why something is uncertain. I'll talk a little bit more about that. So the idea here is that basically we train M independent models. So we have some kind of data set, we train one convolutional network, we train another one, and so on until we have M models. And then we get a new sample, and we want to know what's important for classifying this this time series and how certain are we of this explanation. So we pass the image through all models, we get a prediction from all models, and then we use this class activation mapping method to get the explanations. And then we get 10 explanations. And then we can take the mean and the standard deviation across the explanations. And what I mean that ensembles are kind of intuitive is that if all models in the ensemble indicate that a time step is important, well, probably it's important with a high certainty. But if there's only like one model in the ensemble saying that this time step is important, well, it might be important, but we're highly uncertain of that importance. And also in this paper, we show how you can use these uncertainty estimates to kind of get clearer explanations by filtering out uncertain samples, uncertain explanations. So yeah, let's just move on and look at an example. So this is an example where we have a time series, which are blood measurements. And these are taken from patients that have undergone surgery. So this is a data set from the university hospital here in Tromsø. And the task is to identify patients that get an infection after surgery. So there's always like a risk of contracting an infection after major surgery.
Christopher?
Yes.
I just have a question here. Do you want to just?
Yes.
Yeah, I think. Maybe just come a little bit closer.
Yes, I was just wondering, when you say that you train an independent CNN models,
yes.
Do they vary in terms of architecture, or is it like the parameters in the models that are different?
So it's the same architecture, but they have a different random initialization. So
okay.
You will kind of end up with...
So basically everything, the parameters and everything is the same, but you just use a different initialization for the weights.
Yeah, so the kind of final weights will be different across all the models, but they will perform the same task.
Yeah, okay, good, thanks.
Yeah.
Thanks.
Yes, yeah, so in this case, yeah, we want to identify infections in blood measurements. So we have trained an ensemble of 10 convolutional networks. And this is the results from, so this is an example of one patient in the test set. So the first plot shows so these are the blood measurements. And then the first plot shows the mean across the ensemble. So green indicates that a time step is important, and the more green it is, the more of the ensemble. Okay, so green indicates importance. And then the second plot shows the standard deviation across the ensemble. So these are kind of time steps that are highlighted as important, but not all models in the ensemble agree. And then the last one is this uncertainty filtered one I talked about. So basically you can see that all the time steps that are uncertain are kind of filtered away, and you're only left with these 2 time steps. So as I mentioned, kind of time series is not always as easy to interpret as images. So we talked to kind of a physician who's familiar with this kind of data. So these blood measurements are of something called C-reactive protein, so CRP. And it's known to be highly correlated with the risk of an infection. So we were kind of told this, and that's okay, that's fine. And then we were looking at these results, and we were thinking, okay, but if CRP is highly correlated with the risk of an infection, why isn't these first time steps being highlighted as important? After all, this is where we have the highest increase in CRP. But so the physician explained to us that actually after surgery, it's very common for almost all patients to have an increase in CRP, because it's kind of the body's response to when you have a wound to kind of try to heal the wound. So this wouldn't discriminate between healthy and sick patients. On the other hand, if you see an increase in CRP after like 1 or 2 weeks after surgery, that is typically a much more clear indication that you might have an infection brewing. And in this case, you can see that if we look at the uncertainty filtered scores, that around day 11 and 12, where you see this increase in CRP, that's what's being highlighted as important. So in this case, it seems like the networks have been able to learn like some good characteristics of the time series. I have another example, but how am I doing time-wise? Is this, am I running?
You have about, I would say 10 minutes and then questions.
Okay, well, okay, then we will do okay, just quickly do this example. So this is another data set. So these are of echocardiograms. So basically, each one of these, you can imagine that as being a heartbeat. And the task here is to try and locate what's known as myocardial infarction, or as probably better known as heart attack. And in this case, so from the first image of this mean across the ensemble, you can see that, okay, there's a lot of time steps here being indicated as being important, but there's also a lot of uncertainty associated with a lot of them. So if we filter out all the uncertain samples, then we're only left with this increase in the time series. And this is also somewhere we kind of we had to consult the clinicians, which kind of told that this kind of jump in the echocardiograms is very characteristic of the of people having a heart attack. So also in this case, it shows that yes, the model is able to identify like sensible features, and also kind of shows that if we use this standard deviation or the uncertainty to kind of filter out uncertain time steps, then we get much more cleaner visualizations.
I just have a quick question.
Yep.
So these two examples have been really nice, because you have like these 2 time steps that seem to have less variation or smaller standard deviation. But what happens if you kind of have uniform, high standard deviation over your whole time series? I mean, what do you do then?
Of course, I mean, I've picked examples where things look nice. There are, of course, cases where things doesn't work out really as nicely. But the way we kind of filter these out, you have this kind of threshold, and of course you have to pick this threshold. And there are different ways you can do this. The way we do it in this case is that we take the mean of the standard deviation. So imagine that you just take the mean value of all of these. Mm-hmm. And then we filter out all of them that are kind of above this mean value. So if you have kind of a uniform noise across here, I guess you would have some fluctuation. So you would have it's kind of adaptive. So you would always filter out something, but it wouldn't necessarily look as nice as in this case.
Yeah.
So it's kind of, it's not perfect, but you kind of have to pick a value.
Yeah. Okay.
Yeah. Yes. So I think, I think I'll just start wrapping up. So I hope that I've kind of convinced you that interpretability and uncertainty can be very useful tools when working with deep learning models. I often, if it's not even the goal, I use it when I try to develop models just to see if we're learning sensible things. And I think also in the context of medical data, it's very important just to be able to create like trustworthy models. If these things are going to go into production, you need these kind of things if any clinicians or other people who use it will actually find them useful. At least it's my opinion. And with that, I will end, and thank you for your attention.
Thank you very much. So we have some time for some questions. Are there any from the Zoom audience that has been very quiet and? So I have another question. It seems like your method, or at least this type of method, works really well. But do you have sort of additional research that you want to do now? Like, are you continuing with this in this area, or are you going to kind of branch off into something else?
I think there's 2 points that we wanted to look into. So maybe if people paid good attention here, they noticed that both of these time series are univariate. But when you want to work with multivariate time series, you get this cross dependencies between the different time series, which in our experiments or experience proved a little bit challenging. So it's not always easy to kind of, because then you get much more complex relationships.
Yeah.
So that's something we kind of, we would like to extend it to those cases. And then, as I mentioned, I've been working a bit with unsupervised deep learning, and interpretability in unsupervised learning is not very well explored. But I think it could be interesting because if you do some kind of clustering, it would be very nice to be able to see what, okay, so we clustered a group here, what's kind of the characteristics of this cluster. So these are kind of things that we're working on and would like to work further on.
Cool. Yeah, we have one more here.
For this Monte Carlo dropout, how many iterations do you do? Typically as well 10, or you do much more images?
Yes, so it's a little bit what I usually do to kind of try to decide how many passes is that, okay, I take a sample from the validation set, and then I run it like many times, and then I try to see, like, plot the standard deviation estimates as you do more iterations and see when it stabilizes. So then you can see, okay, if most of them stabilizes after 20 iterations, then we'll stop. But if you have very noisy data, maybe you need like 100. So it's I don't have like a good like standard value, but try between 10 and 100 and see how things look.
For one validation sample?
No, like sample, like, I don't know. It depends on kind of data, but maybe like 100 samples, and then try to see how the curves change. Did it make sense?
Yeah, makes sense. Thanks.
Yeah.
Okay, so I primarily see this as a useful diagnostic tool. You get a positive classification and you want to know why. And so you look at it. But I can imagine there are cases of false negatives where you do not classify something as existing. And is there a flip side of this? Is there an ability to use this methodology or something related to it to say, and here's why we said there wasn't anything present?
Yeah, that's a very interesting.
Just to continue, because if you go a few slides forward in your time series, right? Any one of these.
Yep.
Great. Go back one to slide 14. No, sorry. Yeah. So great. You've got a big dip.
Sorry. This
yep.
one. Sorry.
Right. We got there.
Yes.
You got a big dip between 110 and 130. And so I can imagine if I was actually working with medical professionals and I wanted to like sell them my model so that they really trusted it, honestly, what I would do is I would trawl through your data using all these CNNs, discovered that really there's one feature. Is there a big dip after time 80? And then I would have created a model which was a very simple logistic regression of was there a big dip, was there not a big dip? And that's the model I would have honestly given to a medical professional, because then everybody understands exactly why what they're looking at is there. And so then it's very easy at that point to say, we said 0 because there's no big dip. And so I'm wondering, is there anything, how do you use what you've learned about when you say that there is something there to say, and this is why we said there was nothing there?
So, okay, so let's see. It's a very, very good point. Let's see if I kind of understand correctly. So in all of these cases, I've shown cases where you have kind of, okay, so you have one class and then we predict the correct class. But what if we looked at the explanations for like a class that isn't present? Is that what you're kind of getting at, or?
Yeah, or sure. Yeah, if, I mean, in this case, it's either, you're worried somebody's gonna have a heart attack. You've got an automatic thing that's monitoring these people. And when your model goes off, then you do a preventative measure, and then somebody does have a heart attack and your model never went off, and you want to do it's a loaded term here, but a post-mortem on why your model didn't go off. Okay,
now I understand what you mean. Okay, yeah, so if the model doesn't go off and you're like, okay, so then you can check the explanations to see, okay, what made it not go off.
Yep.
Yeah. I think it's an interesting point, because it's when there's something there, there's always something to kind of detect. But when there's nothing there, it's kind of hard to, if you have an image of a horse, it's like, okay, a horse is there. But if there's not a horse in an image, it's very difficult to indicate why is there no horse here. Like you would either have to say that what you want is basically that it shows that nothing is important.
Yeah.
So I think it's kind of, we haven't looked too much into how it kind of works on when the class isn't present, but it's a good point. I don't have a good answer for you.
Your trained models you can trust your trained models. The better the models, the most you can trust your explanations. If the model is crap, then don't even look at the explanations, because they're not going to be. So if it has some false negatives a lot, perhaps it's not even worth to look at the explanations themselves.
Yeah, so the comment here is just maybe you have to monitor your false negative rate, and if it's too high, then the rest of these exercises might not be worthwhile.
That's a good point, that you could have some kind of criterion like that, and of course these interpretability techniques can be kind of not like a false security, but let's say you make a wrong prediction and then it shows something is important. I mean, it has picked up something in the image, and then you're like, okay, it's because of this, so it probably makes sense. But I think it's not. We can't just blindly trust them. Even with these things, there's still work to be done in that sense.
If I can give a comment, so if this was the heartbeat, if it was a time series of a heartbeat, and this interpretability just tells us which part is important. And now if you ask, why is this patient dead? It's just because there's no heartbeat. So then every time step would be equally important. We're lacking, it's a lack of heartbeat, and it's not only after 80 milliseconds, there's really nothing there. So every time step would be equally important, and then this sort of explainability won't give us much.
No, I think that's also a good point, because okay, if every time step is important, then none is important. If you see what I mean, if you just have a 0, then it's you flatlined, and then the model says, okay, all of these zeros are important. Then it's kind of Yeah, I agree. Then it wouldn't make much sense. So,
but
I guess also
this is typical for all the all parts of XAI or explainability, is that it doesn't really provide the explanations that we would ask for from a doctor. It's just, it gives us some part of an explanation. This sort of explanation tells us which time steps are important. It doesn't give us the causality and the reasoning, and we could ask for much more. So this is part of the solution, and there's potentially other things we could say as well.
I think that's also a good point, that like often you hear the distinction between interpretability and explainability. So interpretability is these kind of things where you get interpretation of your prediction, but explainability is more that, okay, so there's a polyp here, and because of these things with the polyp, that is dangerous, kind of. It's a much more difficult problem. And I agree that there's kind of, so I mean, these techniques are very useful for us that are developing models, and they can also become very useful for people who want to use them. But I agree that there's still a kind of a way to go to provide like really useful explainability methods.
Great. Well, we could thank our speaker one more time, and yeah, we'll have another Big Insight lunch in 2 weeks. So see you then. Thanks again, Christopher.
Thank you for having me.